Next up, we've got Erica and Seoyoon, who I have a very special connection with because I have already interviewed them in the MLOps community podcast. And I heard all about what they're going to be talking about. I'm so excited to actually see the talk now. Since the interview, I've just been like waiting and frothing at the mouth to see what you all talk about. So it's great to have you, Erica and Seoyoon. Good to see you all again. Welcome to the Apply conference.
Thanks.
Yeah, thanks. Good to be here.
So I will let you all take over. And just so, yeah, I mean, I think everybody can read, but they're going to be talking about model calibration in the Etsy ads marketplace. That's it. It's all yours. The floor is yours, Erica and Seoyoon.
Okay, well, thank you. It's great to virtually be here with all of you. So Seoyoon and I are going to be talking about a topic that we have thought deeply about and worked on for the last year, which is calibrating machine learning models. And we're going to be telling you about our journey calibrating all of the models in the system for Etsy ads. So that's a talk, but widely applicable to any sort of ML system. I imagine most of you know what Etsy is, but just to give a little overview of the company, it's a marketplace, a global marketplace for unique and creative goods. It was founded in 2005, went public in 2015, and is headquartered in Brooklyn, but has offices all around the world. They sell over 100 million unique items on the site, and some areas that the company uses machine learning in is product search, user recommendations, and on-site advertising. So I pulled a listing just to give you a sense of the sort of fun, wonky things that you can buy on Etsy in celebration of Valentine's Day, which is coming up on Monday. If you want a very cute melting heart mirror for the low price of $14.99, this is the kind of stuff you can buy on Etsy, along with 99 million other things. So the system that we, Seoyoon and I have worked on is it's the ad product, the on-site advertising product. It's called Etsy Ads. And it's a product or a service that sellers can choose to sign up for. The way it works is that if they choose to sign up, they set a daily budget, an amount of money that they want to put towards advertising every day. And when a buyer comes to the site and searches for something such as heart mirror, the ad system will return an ordered list of items, of listings that ideally are relevant to the buyer and relevant to that particular query. And then if a buyer then clicks on one of these listings, the seller whose listing that is gets charged a small fee and for the promoted click, essentially. And Seoyoon will go into this more in the following slides, but that fee that is charged is dependent on a lot of things. It's actually calculated at request time, and it's set via a second price auction that we run in the background.
Great. Yeah, so to understand the importance of calibration within the Etsy Ads marketplace, we'll first take you through how we rank listings in Etsy Ads. So for every ad request, we score each listing and return the listings with the top scores. Our scoring function is roughly formulated as the score is equal to the predicted click-through rate multiplied by the bid. And the predicted click-through rate is the estimated probability that a buyer will click on the listing, and the bid is the estimated price that a seller will be willing to pay for that click. And both of these components of the scoring function are backed by machine learning models. So in a traditional search system within a marketplace, there's usually one stakeholder, which is the buyer. But in an ad marketplace, it's slightly more complex because there is a new stakeholder who is introduced, which is the seller. So if we take a closer look at the scoring function, we can see that we're actually trying to balance the objectives of both the seller and the buyer. So the predicted click-through rate is actually the objective of the buyer, because it's analogous to the willingness of the buyer to engage with that listing, and it is directly related to the buyer experience. On the other hand, the bid is directly related to the costs, return on ad spend, and the exposure within the Etsy Ads marketplace. So the bid is the seller objective. So within the scoring function, if we place a higher importance on the predicted click-through rate, we are improving buyer experience at the expense of the seller exposure. And if we place a larger importance on the bid in the scoring function, we are improving seller exposure at the expense of buyer experience. So now if a seller's ad is clicked, the sellers have to pay a minimum amount required to keep their position in the ranked list. So what does that mean? So if we take a look at this example over here with the wedding dress query, we can see that 2 listings are ranked. So the first listing, which is this white wedding dress listing, can be seen to have a predicted click-through rate of 0.5 and submits a bid of 60 cents. And since the score is calculated as the predicted click-through rate multiplied by the bid, it obtains a score of 30. And the orange wedding dress listing has a predicted click-through rate of 0.3 and submits a bid of 80 cents, so its score is 24. So you can see that the white wedding dress listing is ranked higher than the orange wedding dress listing because it has a higher score from the formula. And we can also see that if a buyer clicks on the white wedding dress listing, it's actually charged only a cost of 48 cents rather than the full bid of 60 cents. That's because the white wedding dress listing only needed to bid 48 cents in order to outrank the orange wedding dress listing. And this type of cost calculation is known as a generalized second price auction. So that goes to say that if the second best listing or the orange wedding dress listing had a different score, the white wedding dress would have to pay a different cost. So if we take, for instance, the orange wedding dress had a higher predicted click-through rate of 0.35 compared to the original 0.3, then its score would increase to 28 from 24. And as a direct result, the white wedding dress would have to pay a cost of 56 cents rather than the 48 cents in order to keep its position in the list. So from the previous example, you can see that the predicted click-through rate and the bid have a large importance in ad ranking and the cost charged to sellers. As a matter of fact, the variance of these model scores impacts the relative importance between the click-through rate and the bid components in the scoring function. So take, for example, if we look at these distribution graphs, if our bid was constant and our machine learning models were just submitting 1 bid and there was 0 variance to the bid, our score would be dominated by the click-through rate component. On the other hand, if the click-through rate model only outputs 1 single number and there's 0 variance, you can see that the score would be dominated by the bid. With these 2 different examples, you can see that a larger variance within these distributions of scores affect the scoring function, and it places more importance on the distribution with a larger variance. So if you see this final graph here, if there is variance between the click-through rate and the bid distribution, the score is just a product of the 2, and the distribution with a higher variance will have more importance within the scoring function. So now what affects these model distributions? It can be affected by a variety of many different factors. One important factor is a sampling of training data. Take, for instance, our predicted click-through rate model, where we are trying to predict an event that rarely occurs. Take, for example, within the Etsy ad system, the click-through rate might be 1%. In those cases, a machine learning model can kind of cheat the system by predicting the negative instance or non-click 100% of the time to achieve a 99% accuracy rate. So in order for us to help the model distinguish between what a positive example is and a negative example is, there are a variety of sampling techniques where we could either downsample the negative instances or upsample the positive instances so that the model learns a relationship and knows what features lead to a positive instance or a negative instance. However, although that improves the distinguishing capabilities of the models, since we're changing the underlying makeup of the training data, it also influences the output distribution of these models. Other factors that affect the distribution of model scores is the model architecture. If we change the algorithm of the machine learning model from, let's say, logistic regression to boosted trees to neural networks, the output model distribution is significantly changed because of how the loss function is constructed within each of these algorithms. Other techniques such as weight decay and batch normalization has been shown to also affect the output model distribution. And finally, the model complexity or the size of the model also affects the model distributions. If you look at the graph to the right, you can see two real predictions of two of our predicted click-through rate models within our system, where we were trying to migrate away from a gradient boosted trees model, which is shown in the graph in the blue, to a deep neural network model, which is the graph in the orange. And as you saw from our examples before, changing the distribution will change the variance of these distributions and also affect the weighting of these components within the scoring function. Now, the instability in these model distributions every time we iterated on a model significantly slowed down model development. And that's because, as we said before, the cost charged to sellers and the quality of the ads shown to buyers are heavily dependent on the output distributions of these models. In order to stabilize these costs and the buyer experience, we start to introduce manually tuned parameters into our scoring functions to kind of fit the distributions to something that would stabilize these factors. So previously we mentioned that there was a scoring function, which was simplified from predicted click-through rate multiplied by the bid. However, with this new system, the real score was actually a function of the predicted click-through rate, bid, and a set of three constants, alpha, t, and b. The alpha constant was an exponential constant, which was placed onto the predicted click-through rate to weigh the components of the predicted click-through rate and bid differently. So as we increase the alpha constant, we would weigh the click-through rate more in the system, and as we decrease it, it would weigh less. The t and the b constants were placed actually on the bid component to manually fit the distribution to a distribution where it would stabilize the cost. So with the introduction of these different parameters, it became difficult to decouple the impact of the model improvement from the impact of tuning these constants and the scoring function. So, and as a result of these constants, we had to spend extra time in the experiment cycle to tune the scoring function and the constants. So a typical experiment cycle looked like this. We would first iterate on a model until we would find offline improvement gains. Then using these new models, we would simulate an offline auction to determine if there are shifts in cost charged to sellers and the buyer experience. If we did notice a significant shift to costs and quality of the ads return, we would then tune the parameters and the scoring function in an offline manner until we came to a set of constants that we were happy with experimenting online. And then with those parameters, we had to tune those parameters once again online because the offline results are not directly related to the online business metrics. So after fine tuning those scoring function and the parameters, we would then launch the experiment and rerun this entire experiment cycle. So one thing was that these scoring function tuning steps took maybe from days to weeks to even months at certain times, and took valuable developer time into this, something that didn't bring too much value or any learnings into our system. So ideally, we could cut off these two steps from our experiment cycle and leave it to just model iteration, offline auction simulation, and experiment launch. So what we needed to do was that we needed to stabilize our model output distribution so that we don't have to manually fit these distributions to something that would stabilize costs and the quality of ads. And the answer to that problem was calibration. So calibration is a machine learning technique that's used to fit the output distribution of a model to an empirical distribution seen in the system. And one nice property of calibration is that it preserves the order of the original scores. So it doesn't affect the main metrics or offline metrics such as AUC or NDCG of your models. So if we look at the graphs below, on the left-hand side, it's an actual graph of the predicted click-through rate model that we had, where it output a distribution that looks like a bell curve. But in actuality, within our system, the distribution looked more like a power law or log normal graph seen in the empirical distribution side. And in order to kind of transform that prediction distribution to something that resembles the empirical distribution, we just calibrate that model. So why this works is because the empirical distribution and the buyer behavior is pretty stable day to day, where you won't see like 1% click-through rate in one day and then like 10% click-through rate the other day. Since the empirical distribution is extremely stable day to day, we can calibrate our models to output a distribution similar to the empirical distribution, and then that output distribution wouldn't change that all too often. So if we make modeling improvements on the underlying model or change like the model algorithm from logistic regression to deep neural networks, we could force all of these models to output the same distribution. And added benefit of calibration is that the model predictions now become interpretable as probabilities. So the guarantees of interpreting the predictions as probabilities and the stability of these probabilities unlock added benefits, which we'll go into later, where we can start to use them in downstream systems. So we wanted a lightweight method to validate calibration was right for our marketplace and to ensure that it wouldn't affect like the entire system in a drastic manner. So we decided to use Platt scaling as a lightweight method to validate this. So Platt scaling is a parametric version of the sigmoid function, and it transforms raw outputs of a model and uses that features to an additional logistic regression layer. That logistic regression layer learns 2 additional parameters that transform the raw outputs before transforming the outputs into probability space. One thing to know about calibration is that we want to keep the learnings from the original model. So when we train the calibration layer, we want to freeze the original weights of the model. So take, for instance, this sigmoid function on the right-hand side. It's the regular sigmoid function that allows us to transform raw outputs of a model ranging from -infinity to infinity to a prediction ranging from 0 to 1. Now for Platt scaling, you can see it's a minor variant of the sigmoid function where we introduce the constants A and B. So the A constant affects the width of the distribution. And as you can see, if we increase the magnitude of the A parameter, we tighten the distribution. And if we decrease the magnitude of the A parameter, we widen the distribution and increase the variance. On the other hand, the B parameter essentially translates the distribution left and right. Now, we found out that calibrating the models with Platt scaling was extremely easy. On the left-hand side of this diagram, you can see our old workflow where we would train a fully connected deep neural network using some downsample training data and then attach a sigmoid layer to transform the raw outputs to a prediction space. In order to calibrate this model, we basically took the old model, just froze the weights, attached a Platt scaling layer on top of our previous deep neural network before the sigmoid activation layer. And then in order to train that Platt scaling layer, we just used a holdout set of calibration data. And to show you how easy it is, here's a screenshot of the implementation in TensorFlow. Where you can see the constants A and B are trained, and it just modifies the raw outputs of that model. Now with calibration, it required a little minor adjustment to the ETL workflow and the model training workflow, because we needed a separate holdout set that contains the empirical distribution in order to calibrate this layer. So in this diagram, you can see this was our old training workflow, where we would train an uncalibrated model by using the downsample training data, which has a distribution uncharacteristic of the actual system. And then we would evaluate that model using the empirical data set. Since the model was trained using that downsample data set, its predictions would resemble a distribution close to the training data. Now, in order to calibrate this model, we had to partition the evaluation data set because the evaluation data set is the one that contains the empirical distribution. When we train the model, we train it regularly using the downsample data set so it can distinguish between positive and negative examples. But then when we calibrate the model, we use the empirical distribution within the calibration data set. And as a result, the calibration model will now output predictions that resemble closer to the empirical distribution. Now, the question is, how can we assess or how can we evaluate how well calibrated a model is? And a simple way to assess how well calibrated the model is by computing the calibration ratio. So the calibration ratio compares the average of the predictions against the actual rate observed in the system. So a ratio of greater than 1 indicates that your model is overconfident, and it's outputting predictions that are greater than what is seen in the system. And a ratio less than 1 means that your model is underconfident and it's outputting values that are less than what is seen in the system. Now, although this metric is great for a general overview of the model, you might want to know in which prediction ranges the model is performing better or worse in terms of calibration. So we could actually compute the calibration ratios across more granular prediction intervals. So in order to do this, we would bin our predictions across specified intervals. In our example here, we're separating it out into 4 different bins, equally spaced 0.25 apart. In our first example here, we have 4 negative instances where there were no clicks, and these are the outputs of our machine learning model. If we average the predictions and the labels, we get an average prediction of 0.1 and an average label of 0 within this interval. If we do this in the next bin, you can see that there's 1 positive instance and 2 negative instances. And if we average the prediction and labels, this is the result we get. And furthermore, if we just complete this exercise across the next 2 bins, you can see these are the average predictions and labels across these 2 bins. Now, you can imagine we might want to form more granular intervals. Rather than 0.25, maybe we want to make 100 bins and space them out 0.01 apart. In that case, looking at these average predictions and labels might be hard to distinguish where your model is under or overperforming. So we can construct what is known as a reliability diagram. So basically, the reliability diagram plots out the predicted probability against the observed probability across all prediction intervals. Now, if we take, for example, some of these points we saw before in each interval bin, we can plot these points out within this reliability diagram. Now, as you may know, you can see that there's a blue line, which is the identity function across the reliability diagram. And if a point lies on that identity function, it means that the model is perfectly calibrated within that prediction interval. And if a point appears lower than the identity function, it means that our model is overconfident within that prediction interval. And if a point appears above that line, it means our model is underconfident within that prediction interval. So the reliability diagram is a great way to visualize which areas of predictions that your model may be less calibrated in. And we can see an example in the next slide right here. Or the next slide after this, but after calibrating our models, we are able to observe that our models were being calibrated properly. So here's a dashboard showing the calibration ratio metric for our uncalibrated and calibrated models. The yellow dot represents the calibration ratio for our uncalibrated models, and you can see it had a calibration ratio of roughly 33, which means that our predictions were roughly 33 times more than what was observed in the system. So if our system click-through rate was 1%, our model was outputting predictions of 33%. So after calibrating the model with Platt scaling, you can see we achieved a close to an ideal ratio of 1, as you can see in the green dot over there. Now we wanted more granular assessments of calibration within our models, so we generated the reliability diagrams for our models. On the left-hand side, you can see an uncalibrated model where our models were overconfident in predictions across all intervals. But once we calibrated our models, you can see that the dots lie closer to the identity function, where most of the predictions within all intervals were very well calibrated, except for the intervals where we had less data. And if you look at the graph, the prediction ranges where it ranges above like 0.5 or in higher prediction ranges, we have less data because there are less and less listings within that range that have such a high click-through rate. So we don't have enough data within those ranges to calibrate those ranges properly. So now we had to perform a final tuning experiment with these new calibrated predictions because the calibrated predictions significantly changed the output distributions, and the constants were finely tuned to our previous system. And launching the calibrated models as is would cause major disruptions to the seller costs and the buyer experience. But one great thing about calibration was that we were able to simplify the scoring function are removing most of these manually tuned parameters because now the predictions became stable. So while the old score was this function that you see here, the new score became a simple predict click-through rate to an exponent multiplied by a bid. And that exponent is still there because we want to have the lever to prioritize the buyer or seller experience. Now with the stability and the interpretability of these predictions, we're able to apply the calibrated predictions to more product applications. One use case was filtering low quality ads in our system, since filtering low quality ads can improve buyer experience and help long-term marketplace health. Since these are stable, we can introduce thresholds to filter out these low quality listings. And if you look at the query to the right for a wedding dress, you can see that these wedding dress hangers have low predicted click-through rate. And if we place a threshold of 0.06, we will be able to filter out these wedding dress hangers and put out a result set of only wedding dresses. Another use case is that we can flexibly change the page layout based on the quality of ads at a certain period of time. And if we see some type of day where we have ads of low quality, we can push down the ads and show more non-ads on the top of the page. And if we sense that we have higher quality ads at request time, we could show them at the top of the page. And finally, if we have a comparable metric between the non-ads and the ads, we can actually blend the results and show it in a non-fixed order. And thank you for listening to our talk. This project was a year-long project from inception to completion. Couldn't have been done without my manager, Erica, and my entire team. And it was a very fun project. And as a reminder, please calibrate your models, and we'll take questions if you have any time.
Yeah, I want to jump in and ask a few questions that I'm seeing coming through Slack, which are pretty awesome. And that was a great talk. It did not disappoint. So congratulations. Thank you so much for that. The first question that I wanted to ask was, the estimated PCTR seems conditional on the query string. For example, wedding dress versus dresses for weddings. Presumably, the first refers to just white wedding dress, but the later could include bridesmaid dresses. Was the query string used as a feature in any models?
Yes, the query string was definitely an important feature for both the predicted click-through rate and the model that affects the bids. That is the short answer.
Yeah, I'd add on to that too. I'm not sure if this is what the person asking the question was getting at, but the calibration step, we calibrate all our models globally. So everything is calibrated to the average predicted click-through rate, but it is true that different segments, you can segment the traffic by different ways, and we'll have different average click-through rates. And so a follow-up set of work that we want to explore is to calibrate conditioned on various different segments. You can imagine calibrating by platform or calibrating by country. You could try to calibrate conditioned on query, although it's a long tail of many different queries. So I'm not sure if that's what they were getting at, but yeah, certainly query is a very important feature in both the bidding system and the predicted click-through rate model, but it's currently not an input to the calibration step.
And so there's another one in here, and Erica, I see that you answered in Slack, but I think we should just ask it again because people who are not on Slack may want to know this one. From Julian, do you have any processes to deal with pricing inquiries from the seller? Said differently, do you ever have to explain how the fee placed on the seller was figured out?
Yeah, that was a great question. So I put this link in Slack a few times. We did write a blog post about it. Maybe the short answer is that sellers do have a dashboard available to them. We give them a bunch of data and information about their campaign. We tell them which queries they're ranking for, what listings are ranking for those queries, and the cost, the fee that's associated with that. Unfortunately, with many of these complex ML systems, it's not so easy to exactly explain what's going on, even for us. So we didn't get into this, but it's a multi-step ranking process that determines both the bid price and the predicted click-through rate. And there's a second price auction running, and the entire thing is run on, many neural networks, lots of features in data. So it's not so easy, but I think it's something that the company should strive to get better at, because I think people do deserve to know, how their money is being spent. But it is a kind of classic explainability conundrum with these ML systems.
Incredible. Thank you both for this. I just cannot thank you enough, because when you came on the MLOps community podcast, like someone just said in the chat here, like you literally opened my mind. I had not thought about this. And then funny enough, as life works, I went to a few other meetings that same week, and people were talking about similar problems that they were having. And I said, oh, you may want to check out this talk we just had with Erica and Seoyoon, because the calibration thing might be what you need. So it's perfect. Hopefully it helped a lot of other people.
10 lines of TensorFlow code and a lot of offline experiments. Yeah.
Yeah. And what you didn't mention was the 4-month bug.
Oh yeah. Well, right. Once they fixed their bug that took 4 months, it was 10 lines of TensorFlow code.
Yeah. And shout out to also you for the awesome war stories that you presented in that podcast that we had. So everyone, if you want more of Erica and Seoyoon, go check out their podcast with me on the MLOps community, Spotify or Apple, whatever you watch.